Well, welcome back to our sessions on partial differential equations. And we'll actually have a number of lectures on different types of partial differential equations and different methods of solution. Certainly, it's a very important topic. Most practical applications in engineering seem to involve partial differential equations. Much of physics is written down in terms of partial differential equations. And the interesting thing for a class such as this, which is meant to be an undergraduate class, a survey of computational physics, is that it's pretty easy to solve partial differential equations. Those of you who have taken E&M or fluid dynamics realize how much of a struggle it is to find analytic solutions to these equations. In contrast, it's fairly straightforward and reliable and fast to find numerical solutions. And so we'll show you many of the techniques. Now, I'll warn you, what I'm showing you today, for example, this relaxation technique, is fairly simple. And the other techniques we show for these lectures on partial differential equations are all rather simple. They're not necessarily the industrial strength algorithms that you'll use if you were designing the next generation of aircraft or studying the fluid dynamics within a flame. Okay. For those, you might want more robust, more fast techniques, but they're a little bit harder to get going. And we'll give you an example of that someplace. But the techniques we have today work for simple problems. They're often more than enough. And it gets you started to realize how easy it is to solve these problems. So let's get going. Look at slide number 2. This is our problem. And the problem is, quite simply, we want you to be able to solve for the electric potential, usually V, or voltage, for an arbitrary geometry and arbitrary boundary conditions. In other words, that's the most general solution for any problem that you can specify, which is well determined. Okay? And we can do it. We'll solve for a problem which is, you know what the solution probably looks like, and then we'll vary it so that you don't know what the solution really looks like. But in any case, the technique is always the same. So here's our problem. We have a metal box, this dashed blue line here. We have a little gap on the top, and then we have a metal bar on top of the box kept at 100 volts. And the box itself is grounded, is kept at 0 volts. And you're asked to solve for the solution within the gray region inside the conductor. That's the problem. Okay. Well, we can do it. There's some assumptions we make, even just by looking at this problem. For example, if we look here, we could say, what's happening over here at this opening? Well, the gap could be infinitesimally small, so you can ignore it. If you want to be more physical, say, there's an insulator on this gap, and so it's kept at, it doesn't affect anything. It's a closed problem, and I know what the potential is on that insulator, and we make it very small, so it doesn't have much effect. But we need to have a closed region for the mathematics to be appropriate. So we'll do that. We'll assume the conductor has the same potential every place on it, because that's what we mean by a conductor. Charges are free to move, and they'll move in such a way that the conductor becomes an equipotential surface, all the same potential. Okay. And this is the simulation region we have to solve for. So we will have no idea what the solution is outside of this box. We won't even try to get that. In part, we don't know what the boundary conditions are. But inside the box, we know the boundary conditions. So it's closed. We have Normand conditions, and we can solve that. And when we solve it, if we find the solution, we know the solution will be unique, and it will be stable numerically. Now, those conditions we spoke about on the previous lecture about when solutions are unique and stable really are given for partial differential equations. Now, we here, of course, are going to approximate it in some discrete form and find a solution. But the two are usually interchangeable. In fact, if you look in one of the references, say Morse and Feshbach, they derived the conditions for the partial differential equations by looking at the discrete form, since then they can solve it analytically and geometrically, and it's much easier. So, here's our problem. Here's the box. I'll give away the answer. This is the answer in the figure here. And what's interesting about this figure is one of the things we want you to do in this lecture, this assignment, this project, is learn how to do three-dimensional visualizations. Some of you may have done this already. Some of you may do it all the time. Some of you may not have. So let me review. What we mean by a three-dimensional visualization is the same as a surface plot. That's this surface here. So we have a potential V as a function of x and y. So we make the value of the potential the z value. Okay? So we have the height here represents the value of the potential, and then this is the x and y plane. So you go any place in the plane, such as in here someplace. If you move up, we're over here on the surface. That's the value of the potential v. If we project these contours, which means values where the potential is constant value, onto the xy plane, we get on the bottom here, I'll try to outline one and I'll mess everything up. We have here a contour plot. Okay. Sometimes you can put the contour plot on the surface itself, which is what we have here. That's what these lines represent. They actually all mean something. So this is the surface plot, and notice what it says is that at the top the potential is 100 volts. That's right, that's where the metal bar is. As we move away, so as we move down the box here, x values increasing, that's the same as x values increasing here, and the potential falls monotonically, smoothly, to a value of 0 as it touches the box. So this, immediately we know, satisfies the boundary conditions. There's the little indeterminate parts here where the insulator is. And why do we have that? Well, we just have that because you can't have a conductor at 100 volts, so we have to have some insulator. But we've just made that continuous. And notice how the potential is nice. At the corners here, it's nice and smooth. Nothing unusual is happening. This is our numerical solution that we'll obtain. So let's look at the next slide. So the next slide talks about the theory that we solve. How do we solve this kind of problem? Well, you're asked to solve for the potential in some region of space given a voltage or given a charge distribution. If you have a charge distribution, rho, then we can solve Poisson's equation. And that tells us that the second derivative, Laplacian, of the electric potential, here called U, as a function of, that's a bold x, so that's three-dimensional space, is minus 4 pi times rho, in some units. Okay? If you're solving Poisson's equation in a region of space for which there is no charge density, rho is 0, then we have the simpler form, Laplace's equation. We'll develop the algorithm, the theory for both simultaneously, and then whatever the problem you have, you can use one or the other depending on how it's specified. Okay. And for all, I think for all of the cases we study here, we'll just solve the Laplace's equation or Poisson's equation in 2 dimensions. We could easily generalize it to 3 dimensions, but it's just a little more work, a little more bookkeeping, but 2 is fine. So we express del squared in terms of Cartesian coordinates x and y, and there we have the equations we have to solve. And we're writing it here in Cartesian form. Sometimes you may want to write it and solve it in radial form, but it's actually easier to write down the algorithm this way. We'll just use that. So that's the equation we need to solve. It's a partial differential equation because, not just because we have partial derivatives, but because the function we need to solve for, the unknown u, is a function of 2 variables. And both of these can vary independently. X can vary without y varying, or y can vary. So we have variation in x and y. Okay. If we have Laplace's equation, then we have no explicit charge given in the region where we're solving the problem. I'll say that again. I said it right, though. If we're solving Laplace's equation, there's no explicit charge distribution within the region for which we're solving. However, there must be charge present. If there's a voltage, the charge is present indirectly because the charge has caused that voltage. So the charge is there, but we don't need to include it in the equation. We just use that as part of the boundary condition. So let's get on. How do we go about solving this? Well, we have to look at the next slide. Okay. So the standard way in almost all textbooks for solving Laplace's equation, one of the first methods is some type of Fourier analysis. So this is where, if maybe you can remember when we talked about Fourier series? You probably, and I talked about it, and then I did my rant business about how Fourier series is great, but it's not really an algorithm. Same is true here, but even more so. So this is my rant slide, okay? In the textbook, you can still go out and buy some copies are left, I'm sure. Okay. In the textbook, we go about solving this Laplace's equation using Fourier series, and here's the solution. So we see here the solution is a sum over odd terms, an infinite sum, okay, of what? Of a function of x here, and then another function of y. And so it's a product of those, an infinite sum of those. And that's that's the solution. It looks like an analytic form, but let's remind you of two things. Number one, it's some students think, okay, you solve the Laplace equation analytically by just assuming a product solution. Well, this solution here is not a product solution. It's the sum of many product solutions, but it itself is not equal to a function of x times a function of y. Okay, so it's not a separable problem, as you'd say, okay, but each term is. Second of all, the sum is infinite. So you could call that an analytic solution because we're not doing numerics, but it's not a closed form analytic solution. In fact, not only that, but as you recall about the Fourier series, it converges to a function, not like a power series does, but really in some average way. So this is a solution, but only if you use infinite terms. As an algorithm, so if we say let's cut these sum off, not at infinity, but only go up to some value n, we then have an algorithm. As an algorithm, this is not very good. And I've seen even well-established physicists get very confused by trying to solve this as an algorithm, putting it on the computer, and getting very bad answers. Why is that? A number of reasons. Multiple reasons for this rant. First, the convergence is painfully slow. No one has made this up to work very fast. And if it's painfully slow, you need many terms. You're saying, so what, I have a fast computer. Yes, but the more terms you use, the more round-off error matters. The more round-off error there is, the less accurate your solution. It's hard to get this to be a very accurate solution. For example, in order to get comparable accuracy, you need 40,000 terms in the Fourier series to what our algorithm, which we'll talk to you about sooner or later, you only needed 200 terms. Okay, so that's more than it's more than a factor of 10, and it's much more precise. Furthermore, if you actually try to solve this on the computer, program it up, you're using the sinh function. Well, if you look at sinh, of course, it's e to the plus I x plus e to minus e to the minus I x. Well, n here gets very large. In fact, n goes to infinity, so the sinh function blows up for large n, diverges. And the division here of two sinh functions is finite, but you have to be very careful. You have to approximate that analytically in order to make that division, or the terms blow up. So it's not even, it's not particularly nice. And finally, as we've said, at best, if you get convergence, it's just going to be in the mean square. So if this function has discontinuities in it, unusual properties, it may converge to the average value, but not be very good. It's not very good at corners. For example, this is well-known Gibbs overshoot. If you're not using an infinite number of terms, the Fourier series always oscillates back and forth near discontinuities. And discontinuities do occur in nature. So for example, on this next slide, we see the Fourier analysis solution of the same problem that on the first slide I showed you, which is nice, beautiful, and smooth. And here you see, the answer has this Gibbs overshoot here, where it should be a smooth 100. That's almost a straight line. Okay, should be a smooth 100 across here, and what you're seeing is an oscillation back and forth because of the discontinuity at the corner. It gets smaller in the middle, then it picks up again at the end. And you can see here as well. So this is one of the limitations of Fourier analysis. So you won't be surprised that we won't talk about Fourier analysis anymore. We'll talk about numerical methods. So let's talk now about numerical methods and start off there. Look at slide number 6, please. So slide number 6 gives us Poisson's equation and Laplace's equation. I guess, so I've already asked you to excuse me for my hay fever. Now I'll ask you to excuse me for my French pronunciation as well. So those are how I say it, sorry. So we have this equation, and what we need to do now is write it down in a form so we can solve it on the computer. Often this goes by the term of discretation. So we rewrite this partial differential equation, second order, in terms of discrete variables. Sometimes we'll say we'll solve this on a grid. So we imagine here a grid of x and y values, the boundary conditions here shown in red, and we'll solve it inside at all the blue dots. So that's solving a partial differential equation on a grid, and that's done by discretation as well. Okay. So we envision forming this two-dimensional lattice at x and y, and we will solve ultimately for the potential at each lattice site. If we want some value in between, I don't know, too bad. You can interpolate, or you can add more lattice sites to get closer and closer. But that's the best we can do. That's all right. And there's two basic techniques for differential equations, partial differential equations. One, which we'll talk about here, is finite differences. And in finite differences, we express these derivatives. We'll do that on the next slide. We'll express these derivatives in terms of the finite difference of the unknown u at different sites. Simple as that. So we just write the derivative as finite differences. Another approach, excuse me, known as finite elements, might do something like say, let's find the solution instead for a little square here. And then we find the solution at another little square, here. And then we find it also at some other square here, drawn in some other way, dotted square, okay? And then we could get, say, the exact solution for some square region, and then that's a finite element. And then we match together these finite elements. And sometimes the elements are square, sometimes they could be triangles, depending on what fits in the geometry. And we'll have a separate little lecture on finite elements. In practice, for industrial strength applications, finite elements are more robust. They give you very fast solutions. But gee, they're a pain in order to figure it out. They are often very hard to parallelize, and you have to work pretty much to get the answer. But at the end, it's worth it. But we won't talk about it much. Okay, we'll do what's easy here, get some solutions, then we'll show you a sample case. So that's what we want to do. How do we do it? This is the hard part. Okay? And it's really not very hard, but what we want to do is take that partial differential equation, remember it here, impose it on your mind. We want to write that partial differential equation as a discrete differential equation, discretize it. So we start off, number one here, we start off by using a forward difference approximation for the derivative. And what we're saying here is, okay, we have our unknown u, we know what it is at x and y, and let's say what is u if we move one step delta x forward in space. Well, it's just going to be a Taylor series, the value at x and y plus du dx times delta x. So that's just a Taylor series, which if you want is just a forward difference approximation. Then we have a second derivative and the del squared terms. Fine. We can do this. What if we move back one step? Aha. If we move back one step in space, then the value of the function, and again, remember we said it's a physical observable. Physical observables we know vary smoothly in space and time, because physics does. So it's the value at x and y minus du dx times delta x, and here's the critical part. Again, a plus sign for the second derivative in both cases. So if we add these two equations together, okay, one moving to the right, the other moving to the left. So this is moving to the right of the solution. This tells us how to move to the left. We just add them together, and then the first order terms cancel out, and we're left with an equation, d squared u by dx squared, an approximation, is approximately, that's just the approximation for the second derivative. So you've seen that before, except here we're doing it for partial derivatives. So here, this is the form for dx squared. There's another exactly the same form for dy squared, but it would have, y varying rather than here, x. Okay? So we have that nice form. This is now an expression for the second derivative. X varies one side to the other side, and we subtract off that familiar -2. So it's similar. We just spoke about this recently when we spoke molecular dynamics, when we gave the Verlet algorithm. You've seen something similar before. So this is a second derivative. So if we substitute this expression for the second derivative into Poisson's equation, we get a discrete form of Poisson's equation. Okay, so here we have the d squared by dx squared term on top. That's this guy. And here we have the d squared by dy squared term on the second line. And that's all it is. And there's the -4 pi rho. So that is Poisson's equation in a discrete form. So we could, if we are just a little bit clever, solve that on a lattice, because the lattice are the discrete steps. So this is Poisson's equation in terms of the finite differences of the unknown of the solution. Okay? So now we just have to go ahead and figure out an algorithm how to solve that equation on a computer, and then we have a solution. So why don't we take a break? Okay, because we're going to have to work a little bit to get the algorithm and do some bookkeeping. But it's a good time to take a break. And we'll come back. So, see you soon. Bye-bye.